Welcome to this short course on terrestrial planets. The objectives of the course are to give some information on terrestrial planets, describe some missions and observational techniques which study these bodies, and illustrate this with some results. Terrestrial planets have a solid surface, are small, dense, but not massive bodies. In our solar system, there are 4 such planets: Mercury, Venus, Earth, and Mars. Some characteristics of the planets in our solar system are reported in this table, indicating some orbital parameters. Differences between the 4 terrestrial planets and the giant planets are clearly visible on the size of the bodies and their mass and density. This graph clearly illustrates that even if the different planets do not have identical atmospheres, they are constituted of the same building blocks. On Venus, Earth and Mars you will find nitrogen, carbon dioxide, water, oxygen, but in different relative quantities. So, what is comparative planetology? The idea is to compare different properties of the planets, use them as big natural laboratories studying the impact of different environmental conditions, look at differences and similarities. The objective is to better understand the different physical, chemical and dynamical processes, to help better understand the history and evolution of planets, and finally to better understand the origin, evolution and future of our own planet. A first example of comparative planetology is the analysis of the different relief of planets and what these could tell us on their formation and evolution. This graph shows the percentage of surface having a specific height. One can see that almost all Venusian relief lies within 2 km, confirming the idea of relatively recent global resurfacing. On Earth and Mars, there is a very much more diversified geography, with some of the most spectacular sites like Mount Olympus on Mars, which is the highest mountain known in our solar system, culminating at 24 km. What is also striking is the dichotomy on Earth with the continents and then the deep ocean abysses. And this is indicative of an active tectonics taking place on the planet. Another example is to compare the obliquity and rotation direction. This can provide information on the formation of the planet. For example, Venus and Uranus are rotating in a retrograde manner, very different to the direction of rotation of the other planets of the solar system. Scientists have suggested that Venus and Uranus originally were spinning like all the other planets, but sometimes in their history were hit by massive objects that set them spinning in the other direction. More recently, it has been proposed that the Sun's strong gravitational pull on the dense atmosphere of Venus created atmospheric tides which slowed down the planet and made it turn in the other direction. Presence of seasons can also be deduced from these orbital parameters. A small eccentricity means a more circular orbit, and if combined with a small inclination, like for Venus, of the rotation axis of the planet on itself, this can explain why there is no season on Venus. Inclination of the rotation axis are very similar for Mars and Earth, but the seasons on Mars are intensified because of its orbits being more elliptical, meaning that the quantity of solar energy received will be very different at aphelion or perihelion. The second part of his course will briefly describe observational techniques used by space instrumentation. Nadir observation correspond to instruments looking down to the surface of the planet, either during day, where you have a contribution from the solar being reflected on the surface, during the night, or what we call offset or off-nadir observations. Limb observations can be done again at night, looking directly at the emission from the atmosphere itself, or during the day. A particular case of occultation is occultation, during which the instrument looks at a star or at our sun. I will very briefly introduce the theories of sounding atmospheres, which is based on the description on how radiation interacts with matter, in our case, the atmosphere. Let's consider a very general atmosphere which can absorb radiation. Radiation can also be emitted by this atmosphere since it is lying at a certain temperature and thus can be radiating like any black body. A third mechanism of interaction is diffusion or scattering of light. The Schwarzschild equations summarize the gain and loss of radiation while going through the medium. It can be written as a differential equation or under its integrated form. Radiative transfer modeling means solving this equation, considering the different sources and losses of radiation, which will directly depend on the composition of the atmosphere, its temperature, but also on the instrument and the spectral region probed. Extinction is due to absorption and scattering. Absorption coefficient can be calculated using first principle spectroscopy theory. They will depend on the geometry and symmetry of the molecule, the temperature, the presence of other gases. This graph here shows the resulting absorption spectra for a series of species usually found in atmospheres. As you can see, each molecule is characterized by specific absorption features at different wavelengths, which make their detection possible with spectroscopic space instruments. The position of the absorption features will give information on which molecule absorbs, while the amplitude of the feature will give information on their abundance. Scattering is far more complex. It will depend on the size, form and composition of the particle. Since energy is scattered in all directions, it makes the Schwarzschild equation far more complex to solve. As an illustration, the term describing the scattered radiation is itself an integral on all scattered directions. In the following, I will illustrate the use of the Schwarzschild equation in three very simple cases, none of them considering scattering. First, let's look at an eyesight nadir observation. In this case, the source term is the blackbody emission of the surface of the planet. This is the first term here in this equation. But each layer of the atmosphere also radiates as a blackbody at the different temperature. These are the G terms in this expression. This expression can be rewritten such that what we call weighting functions are made prominent. Those functions are sensitive to where the radiation is generated at the given wavelength. This is why near observation usually make use of several wavelengths which will probe different layers of the atmosphere, as is illustrated in the following slide, where you have an indication of where in the atmosphere, this is pressure or altitude, corresponding wavelength information will provide information on the atmosphere. The second example corresponds to limb observation during the night. In this case, there is no source term except thermal emission from the atmosphere itself, here represented by the Planck function at the different temperature of each layer in the atmosphere. Changing slightly the way the equation is written, one can again define the weighting function, which are represented for typical observation in the plot on the right for different tangential heights sounded sequentially as the instrument probes from the top of the atmosphere down to lower altitudes. Limb observations usually provide high vertical resolution and are sensitive to low abundances. The third example is a particle case of limb observation called occultation, which corresponds to an instrument looking at a star, here the Sun, being a particular case. If atmospheric emission can be neglected, then the equation simplifies itself to the known Beer-Lambert law. Starting now, we will go through the terrestrial planets and describe their main characteristics. Let's start with Mercury. Mercury rotates in a way that is unique in the solar system. The planet is tidally locked with the Sun in a 3-to-2 spin-orbit resonance, which means that the planet rotates on its axis exactly 3 times for every 2 revolutions it makes around the Sun. The surface of Mercury is rocky with a multitude of craters. There are no signs of volcanic activity nor plate tectonics. The temperature difference between day and night comes from the fact that the planet rotates very slowly and that the atmosphere is so thin it does not retain heat. Mercury possesses a thin atmosphere made up of atoms blasted off the surface by the solar wind and striking meteorites. Mercury's exosphere is composed mostly of oxygen, sodium, hydrogen, helium, and potassium. Hydrogen atoms and helium probably come from the solar wind. Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time. It is likely that the magnetic field existing on Mercury is generated by a dynamo effect in a manner very similar to the magnetic field on Earth. This dynamo effect would result from the circulation of the planet's iron-rich liquid core. Particularly strong tidal effects caused by the planet's high orbital eccentricity would serve to keep the core in the liquid state necessary for this dynamo effect. Mercury's magnetic field is strong enough to deflect the solar wind around the planet, creating a magnetosphere. Let's talk about missions, and in particular missions to Mercury. MESSENGER for Mercury Surface Space Environment Geochemistry and Ranging was launched in August 2004 and ended in 2015. The initial length of the mission was 1 year, but was extended much more. At the end, the orbit was closer to the planet, allowing for more observations. This image was obtained by one of the instruments on board, a specific visible and infrared spectrograph. It shows the spectral reflectivity of the planet, obtained at different wavelengths. This gives indication on the composition of the surface. Younger surface materials that are brighter at visible wavelengths and less affected by the processes of space weathering show up in reds, yellows and greens. Materials that may have relatively higher iron contents, though still very low relative to most lunar or terrestrial crustal rocks, show up in blue. Bepi-Colombo consists of two individual orbiters, ESA Mercury Planetary Orbiter (MPO) and JAXA Mercury Magnetospheric Orbiter (MMO). MPO has as primary goals to image and map Mercury throughout its orbit, which is quite distinct from the orbit followed by MMO, which will study Mercury's magnetic environment. Bepi-Colombo needs 9 gravity assist flybys, 1 at Earth and 2 at Venus, 6 at Mercury before it will enter the final orbit around the planet in 2025. The first flyby of Venus occurred in October 2020, and here you can see on the right pictures on the encounter with the planet. There and there. Let's move on to the next planet, Venus. Venus is characterized by a very different temperature and pressure condition on its surface, showing no diurnal variations. Also, from its orbit, one expects seasons to have only small or negligible effects. The planet is entirely covered by clouds, which acts like a barrier between what's happening below and above the clouds. The atmosphere is also characterized by a superrotation at the cloud top. Atmosphere is mainly composed of CO2, while the clouds are sulfuric in nature. There are different layers of clouds and hazes on Venus, characterized by different size and composition of the particles. They have been observed by a variety of spacecraft, the most renowned being the ones captured by Galileo, which made the flyby of the planet in the 90s. The surface of Venus is made up of plains, lowlands and highlands, with plenty of different kinds of features which are linked to volcanic activity. Some words now about missions to Venus. The only remaining spacecraft around Venus for the moment is Akatsuki, which was launched in 2010 and was supposed to get into the Venus orbit in December the same year. However, a technical problem prevented this, and 5 years later the insertion maneuver was tried again, and this time successful. Since then, Akatsuki has made impressive observations of the clouds structure from the IR and UV camera on board the spacecraft. Venus Express is a European Space Agency mission. It consisted of a series of instruments whose main objectives were the characterization of the atmosphere of the planet, from its surface to its interaction with the solar wind. The mission, which was launched in 2005, starting its science mission 1 year later, some months later, and then ending its mission in November 2014, was really a success. It delivered a wide variety of results during these 8 years of operations. In the following, I will only select a very few of them, which are mostly linked to the atmosphere. And in this first example, we show how measurement of one species, atmospheric species, could infer atmospheric circulation that was hypothesized on Venus. At high altitude, the circulation is driven by the sun illumination going from the day side to the night side. CO2 being photodissociated on the day side by UV radiation. Atoms of oxygen are entrained towards the night side of the planet, where a series of reactions convert those excited atoms back to oxygen molecules. In the process, a typical radiation called the oxygen night glow is emitted and could be observed by the instrument on board the mission. Several instruments on Venus Express could characterize the composition of the atmosphere, even going below the clouds using well-defined transmission window in the infrared. Using solar and stellar occultation, vertical profile above the clouds could also be obtained. One of the target gases was sulfur dioxide, which on Earth is linked to volcanism. We observed highly variable SO2 abundances varying in space and in time over long and short time scale. These variations were confirmed by ground-based observation, as can be seen here in the plot below. The plot on the right shows you long-term evolution of the SO2 above the clouds since the early days of Venus exploration. One can see that it decreased during the Pioneer and Venera era and was again high at the start of the Venus Express mission and then decreased again. If one looks more carefully, one can see that in fact this decrease was punctuated by short-term episodic injections. The question is still under investigation to know if those injections are connected to volcanic activity, like Pinatubo injection on Earth, or if they are due to dynamical variability. One of the objectives of the Venus Express mission was also to detect volcanism. VERTIS, one of the instruments on board, measured the spectral emissivity at 1 micron of the surface to study the properties of likely Venusian hotspots, in particular around volcanoes in 3 of the most prominent spots. VERTIS data show anonymous high emissivity values. Those are anomalies because, like on Earth, if you climb on the top of the mountain, the temperature should decrease and not increase as was observed. These high emissivity areas were interpreted as fresh lava flows around volcanoes. Let's go now to Mars. The orbit of Mars is very elliptical. Temperatures on the surface are highly variable, and you have there some indication of the variability. Today Mars is a very dry and cold planet with a thin atmosphere mostly composed of CO2. No liquid water can be found at the surface under today's atmosphere conditions. Mars has attracted a lot of research and visitors since the beginning of space exploration, even if the success rate of the missions is very low. Nevertheless, we have been accumulating lots of information on the planet through space instruments, but also using landed assets like rovers or platforms. As already mentioned, the orbit of Mars is highly elliptical, which explains the difference between the northern and southern hemispheres of the planet. In the south, Extreme seasons are characterized by cold winter and warm summer, whereas in the north season are more temperate with milder winter and cooler summer. This figure here illustrates that on Mars we usually use the solar longitude LS to express the passing of time on Mars. Another asymmetry between the northern and southern hemispheres lies in the topography, the north being mostly low altitude plains while the south elevated plateaus. As already mentioned in the introduction, the highest summit found in the solar system is the Mount Olympus. The northern and southern polar caps are also different, being composed of CO2 ices and water ice in the north. Their latitudinal extension varies with seasons and again differ in both hemispheres. Following the sublimation and condensation cycles of CO2 on the polar caps, the pressure is directly impacted, CO2 being the main constituent of the atmosphere. These curves show the evolution of the pressure at the location of the two Viking landers through one Martian year. The plots on the left show typical temperatures of the atmosphere and compare temperature on the Earth in blue with temperature on Mars in red. On the right, typical temperature on present Mars are shown in the pressure temperature plot, and we can infer from this that no liquid water can be found on the surface today. The atmosphere of Mars is composed essentially of CO2, nitrogen, argon, oxygen, and then trace gases. Dust is an essential constituent of the Martian atmosphere. It is usually more present during specific seasons when the planet is hotter, means close to the perihelion. Sometimes regional or even global storms can take place, impacting widely the composition and circulation of the Martian atmosphere. And you have here a picture of Mars just at the start of a global storm, and here during this storm impacting globally the planet. Usually dust is more present during the warm perihelion season, that is during the spring and summer in the southern hemisphere, as clearly shown here in this graph, which summarizes several years of observation by one of the instruments on board Mars Express. Besides dust, clouds also occur on Mars. They can be of different types, like polar clouds or orographic clouds generated by features on the surface, and in particular the mountains. As their name alludes to, polar clouds are found close to the poles. They are associated to very cold temperatures. They probably influence the amount of water ice that is incorporated and later released in the seasonal polar caps. The aphelion cloud belt occur in the equatorial region, and those clouds play an important role in influencing the seasonal and latitudinal distributions of water on Mars by restricting cross-equatorial water transport. In the following slides, I will focus on the search for methane on Mars. It all started in the early 2000 years when several independent studies revealed positive detection of methane in the atmosphere of Mars. Two surveys were done from Earth using large telescopes, and one was done from the Mars Express mission orbiting the planet. From Earth, methane can be observed using large telescopes associated to very sensitive and high-resolution spectrometers situated, for example, at Hawaii or in Chile. The idea is to take spectra corresponding to the different position of the projected slit on Mars. By the natural rotation of the planet, different observations will be used to map the planet. This is an example of such an observation, where on the top you have a typical recorded spectrum in which the main absorption are due to the Earth atmosphere. After removal of the Earth contribution, the absorption features due only to Mars are visible. Each line here corresponds to a different latitudinal beam sound on Mars. Absorption by Martian water is easily seen, as well as a series of lines which were attributed to Martian methane. Converting those absorption amplitude into abundances, those maps could be obtained, combining all the measurements. A clear maximum of abundance is observed at the equator, reaching about 30 ppb or part per billion. These plots summarize the early observation done by PFS, so on board Mars Express, showing that on the contrary, maxima of abundance were found at the poles. One thing is common to all those observations: they are highly variable, both in space and time. More recently, the SAM instrument on board Curiosity rover made measurements of methane in Gale crater. These measurements are showing that background level, or here, I zoom on the background level, correspond to values which are below 1 ppb, but spikes can occur reaching tenths of ppb. Also, as shown here, the background value of methane is shown to be seasonally dependent, whereas the spikes have still to be understood and are occurring independent on the background seasonal dependence. So why is the methane such a high topic on Mars? Why is it a problem or an issue? This comes from the difference between the observations and the known behavior of the molecule. Models, that is what we know of the chemistry of the species and its interaction with radiation, indicate that if present, methane should be uniformly distributed and that its photochemical lifetime should be long, whereas observations are localized both in time and space and are compatible with a lifetime of hundreds of days, not years. If the observations are correct, this would imply that methane is replenished and that there is a destruction process, although this process is still unknown. Anyway, whatever the final clue or the final truth, what is important is that if indeed we detect methane, that would be the first detection of trace gases linked to life outside of Earth, and absence of detection would be also important because Mars lies in the habitable zone of our Sun. Recently, two independent instruments on board ExoMars Trace Gas Orbiter have tried to detect methane from the Mars orbit. They could not detect any methane. Detection limits were calculated. Basically, that's converting noise into an abundance value. And the observation found out that these detection limits corresponded to 50 ppt, so well below the background values found at Gale Crater. These observations were performed by solar occultation, which, as we will see, is a very sensitive technique, but in the case of Mars, could not probe below 1 kilometer altitude because of the signal being absorbed by dust. Concerning mission to Mars, Mars Express is still active. It's a European ESA mission. It has been launched in 2003 and is still providing a lot of information on the planets and its atmosphere. It is devoted to the study of its atmosphere, but also to the surface and subsurface. It's not possible to enter into all the details on all the existing mission towards Mars, still existing or which were active in the past, so I will only concentrate on a small number of missions. So as already described, the European Mars Express mission. Of interest also for the moment is the MAVEN mission, the Mars Atmosphere and Volatile Evolution, whose objectives are to characterize the solar wind, ionosphere and interaction between them, and to better understand the upper atmosphere. The last mission sent by Europe is ExoMars. In fact, ExoMars is a two-pillar mission. The first element was launched in 2016 and is now in orbit since 2018. The second element, which will deliver different instruments on the surface of the planet on a rover and a platform, will be launched in near future. The role of the first element was to investigate the composition of the atmosphere in search of trace gases and relate them to surface and subsurface. It will also give a global context for the next element. This will consist of a rover and a platform with a multitude of instruments dedicated to the search of traces of life. Particular, the rover will be equipped with a drill which will be able to reach 2 meters below the surface. Coming back to the Trace Gas Orbiter, so the first element of the ExoMars mission, 4 instruments were composing its payload, 2 suites of spectrometer, NOMAD and ACS, 1 high-resolution camera, and a neutron detector sensitive to the presence of water in the close subsurface. In the following, I will show some results obtained by the spectrometers, which are focusing again on the composition of the atmosphere. Solar occultation provides very accurate and high-resolution vertical profiles of a series of molecules. Water vapor is one of them. Water is very important to understand the atmospheric cycles, but also to give clue to the history of the planet. Indeed, we can look at the D/H ratio obtained by comparing abundances of H2O and HDO, a water molecule in which one hydrogen has been replaced by a deuterium. Under high dust content, the atmosphere gets warmer, expanding and training water and dust to higher altitudes, where the water can easily be photodissociated. Hydrogen atoms being lighter than deuterium, they are more prone to escape, leaving more enriched water in the atmosphere, thus increasing the D2H over time. Indeed, today the ratio is 6 times the value found on Earth. This could explain why Mars lost its water. The discovery of the green oxygen line was unexpected. This was done using the UV channel of the NOMAD instrument, looking at the limb during the night. Emission lines due to CO2 plus or oxygen around 300 nanometer can be seen here in those spectra and have already been observed by previous instruments. What is new is the simultaneous observation of the green line at 77 nanometer. In fact, this is the first time that this emission line has been observed on a planet other than Earth. To conclude, I would like to mention that the future, and in particular the near future, will be very busy with a series of missions arriving at Mars in the coming months. For Venus, there are several missions under development that are waiting for final selection. Thank you.